The universe's greatest mysteries are now unfolding on computer screens. This is the frontier of simulated universes, digital sandboxes where we can test ideas about dark matter and cosmic evolution without ever leaving our desks. By the end of this, you will know how to build your own cosmos from scratch. What would happen if gravity were 10 times stronger, or if the very fabric of space had extra dimensions? What kind of universe would you create first? A toy cosmos begins with a simple but radical idea. We are not trying to build an exact copy of our own universe. Instead, we create a digital Petri dish, a controlled environment where we can write the rules ourselves. The first step is to define the blueprint, a set of fundamental laws that will govern this pocket reality. Think of it like the instruction manual for a board game. You decide how many spaces a player can move, what happens when they land on a certain square, and what the ultimate goal is. In our toy universe, we are writing those core instructions. We decide the strength of gravity. We decide if space has 3 dimensions or 4 or more. We can even define the properties of something like dark energy, turning its mysterious push into a simple variable we can adjust with a few lines of code. These models are powerful because they are abstractions. They strip away the overwhelming complexity of our own cosmos to focus on one specific question. What if the fundamental constant that determines how particles interact were just a little bit different? What if the Big Bang unfolded at a slower rate? By isolating these variables in a clean, digital sandbox, we can see their pure effects without all the noise. A physicist once noted that the true power of any model is not in its complexity, but in its ability to make predictions. A simple, well-designed toy universe can often teach us more than a messy, overly detailed one. It was this same spirit of simplification that guided the first great thinkers, philosophers, and scientists who dared to sketch out entire worlds using only the power of their minds and the mathematics of their time. Centuries before the first computer hummed to life, the human mind was already building universes. The philosopher Gottfried Leibniz proposed a stunning idea that our reality is merely the best of all possible worlds a benevolent creator could have brought into being. He envisioned a vast collection of potential existences, each with a unique set of physical laws. This was metaphysical pluralism, a grand philosophical tradition suggesting that the cosmos we inhabit is just one option among countless others. This profound thought experiment was the very first blueprint for a toy cosmos, meticulously crafted from logic and imagination instead of code. It established a radical principle that the laws of nature might not be fixed and inevitable, but contingent and open to variation. That intellectual spark did not fade. It smoldered for generations, waiting for the right fuel. In the 20th century, this philosophical flame ignited modern cosmology, giving rise to the multiverse theory. Scientists began to suggest that what we call our universe might just be one bubble in an infinite cosmic foam, with other regions of space-time operating under completely different rules, perhaps with more dimensions or weaker forces of gravity. These early thinkers, armed only with pen and paper, were the original universe builders. They proved that our drive to simulate, to ask what if, is not a modern obsession with technology but a fundamental part of human curiosity. And that deep-seated impulse was about to find its ultimate tool. That philosophical spark finally found its fuel with the hum of the first mainframe computers. The mid-20th century gifted us with a new kind of canvas, one made of silicon and electricity, where cosmic blueprints could finally come to life. Visionary minds like John von Neumann saw these machines not just as calculators, but as engines for simulating reality itself. They imagined a future where you could model the weather, the economy, or even the dance of the stars. That vision became a reality with the very first N-body simulations. Picture the challenge of tracking how thousands of stars, each pulling on every other with gravity, move through the void. The sheer number of calculations was staggering, far beyond what any computer of that era could handle with raw power alone. So scientists got clever. They developed brilliant mathematical shortcuts, using approximations to represent the collective pull of distant stars, allowing them to simulate the majestic swirl of entire galaxies on machines with less processing power than your modern smartphone. This was the pivotal leap. For the first time in human history, cosmology was no longer just about looking up at the night sky and trying to piece together a story from faint, ancient light. It became an experimental science. We gained the power to run the cosmic clock forward to see how a cluster of galaxies might evolve over billions of years, or rewind it to witness the possible origins of the large-scale structures we see today. With this monumental power now at our fingertips, what are the actual ingredients you would need to build your own cosmos from scratch? Building your own cosmos requires a set of master dials, numbers so fundamental they define reality itself. These are the constants of nature. Think of them as the immutable settings of the universe, the unchangeable numbers that dictate the strength of gravity, the maximum speed of light, and the forces that hold atoms together. In our reality, these values are fixed, but inside your digital sandbox, you hold the ultimate creative control. You can turn these dials yourself. Crank up the gravitational constant to 10 times its normal strength. Suddenly, the gentle pull that holds our solar system together becomes an irresistible cosmic vise. Galaxies would collapse into existence far more quickly, forming dense, tightly packed islands of stars. Now turn another dial, the fine structure constant. This one number governs how atoms interact, how electrons orbit nuclei, and ultimately how chemistry works. Make it just a little larger or smaller, and the delicate nuclear reactions inside stars might fail. The complex molecules necessary for life might never form. This is where a profound idea comes into sharp focus, the Anthropic Principle. It suggests that the only reason we are here to observe the universe is because its constants happen to fall within a very narrow, life-permitting range. Our existence is a product of this specific cosmic recipe. By tweaking these numbers in a simulation, we are not just building worlds, we are directly testing this principle, asking the ultimate what-if question about our own place in the cosmos. And once you have set these fundamental dials, you need a stage for the drama to unfold, a framework of physical laws to bring your numbers to life. With the fundamental constants set, your next task is to write the very rulebook of reality. These are the laws of physics for your toy cosmos, the dynamic principles that will govern everything from the orbit of a planet to the expansion of space itself. You have a profound choice to make here. Do you implement the known laws of our own universe, like Einstein's intricate equations of general relativity that warp space and time around mass? Or do you invent something entirely new, crafting a universe where time flows in two directions at once, or where a fifth fundamental force binds matter together in strange, crystalline structures? This creative freedom, however, comes with a practical constraint: the immense computational power required to run these simulations. The beautiful, complex curvature of spacetime in general relativity demands staggering processing resources. This is why so many pioneering simulations rely on a simpler, more tractable framework, Newtonian gravity. It is a powerful approximation that, while not accounting for the subtleties of relativity, still accurately captures the gravitational dance of stars and galaxies on cosmic scales. This act of simplification is not a compromise but a deliberate design choice. By stripping physics down to its most essential rules, you are forced to confront a deep question: which laws are absolutely necessary to produce a universe that looks anything like our own? Does life require the specific warping of spacetime, or would a simpler force of gravity be sufficient for galaxies to form? You are not just building a universe, you are testing the very foundations of our own. And with this rulebook in hand, you are ready to construct the spatial arena where your cosmic drama will unfold. The stage of your universe is its spacetime geometry. You have the power to define the very shape of existence. Will you build a flat cosmos, an infinite and uncurving grid where parallel lines never meet, much like our own universe appears to be on the grandest scales? Or will you choose a closed geometry, a universe that curves back on itself like the surface of a sphere? In such a world, a spaceship traveling in a perfectly straight line would eventually return to its starting point from the opposite direction. Then there is the open, hyperbolic universe, a cosmic saddle shape that stretches into a wild, divergent infinity. This fundamental geometry is not just a background, it is an active player in the cosmic drama. In computational terms, this is all encoded in something called the metric tensor. Think of this as the ultimate set of instructions that tells every particle, every photon of light, how to move through the space you have created. It defines the shortest path between any 2 points, the very rules of motion. For simplicity, you might start with a 2-dimensional universe, a flatland where complex interactions are easier to calculate and visualize. Or you could be ambitious and construct a 4-dimensional space, a realm where hyperbeings could perceive shapes and connections utterly invisible to us. This choice of geometry dictates the ultimate fate of everything within it. A closed universe might eventually collapse in a big crunch, while an open one would expand forever into cold, dark isolation. It even determines how matter clumps together, influencing whether galaxies form vast, delicate webs or dense, isolated knots. With this cosmic stage firmly constructed, the theater is empty and waiting for its actors. Your next decision is perhaps the most creative of all. You must seed the initial conditions, the primordial state from which your entire cosmos will unfurl. Every universe needs a starting point, a first moment that contains, in potential, every galaxy and star that will ever be. In our own reality, this was the hot, dense plasma of the Big Bang, a nearly uniform soup rippling with infinitesimal quantum fluctuations. These tiny wrinkles in density were the cosmic seeds, and gravity was the sculptor that patiently amplified them over billions of years into the vast galactic web we see today. In your simulation, you hold this ultimate power of genesis. You can define that first spark. Will you begin with a perfectly smooth, homogeneous distribution of matter, a blank canvas of pristine uniformity? Or will you inject your own patterns of density, carefully placing regions that are slightly hotter and denser than others, like sprinkling seeds in a garden? This is exactly what cosmologists study in the afterglow of our own Big Bang, the cosmic microwave background. That famous map of the sky is essentially a baby picture of our universe, a snapshot of its initial conditions frozen in time. By controlling these seeds in your digital universe, you are not just setting a starting line, you are writing the first paragraph of a billion-year epic. The specific patterns you choose will directly dictate the future. A perfectly smooth start might lead to a sterile, featureless void, while a universe seeded with the right kind of fluctuations will blossom with intricate clusters and filaments of galaxies. With the stage set, the laws written, and the seeds planted, the simulation is ready to run, setting in motion the grand, dynamic process of cosmic evolution. The clock starts ticking, and your universe begins to live. From that single, seeded moment, every particle now feels the push and pull of the forces you defined, and the entire system must evolve forward in time. This continuous dance of motion is simulated through a process called numerical integration. The computer cannot process an infinite, flowing river of time, so it breaks that river into a vast number of tiny, discrete steps. It is like creating a cosmic flipbook. At each step, the machine calculates the position and velocity of every single particle, applying the gravitational forces and physical laws you programmed, then snaps a picture. It then moves every particle forward by that minuscule amount, recalculates all the forces for the new arrangement, and snaps the next picture. String billions of these snapshots together, and you get a movie of cosmic evolution. The size of these time steps is a critical choice. Smaller steps create a smoother, more accurate movie, capturing every subtle gravitational nudge, but they come at a steep cost, demanding exponentially more computing power and time. Larger steps make the simulation run faster, but risk introducing errors like a flipbook with pages missing, where the motion becomes jerky and the physics unreliable. This delicate trade-off between precision and pragmatism is the core challenge of every simulation. This challenge becomes astronomical when you are tracking the gravitational pull between billions or even trillions of individual particles. Calculating the force on every single particle from every other particle would require an impossible number of calculations. This is where a stroke of genius comes into play, with algorithms like the Barnes Hut method. This approach treats a distant cluster of thousands of stars as a single, unified object. Instead of calculating the individual pull from every star in a far-off galaxy, the simulation approximates their combined gravity as coming from one point. It is a brilliant shortcut, like estimating the weight of a forest by looking at a single, representative tree. This approximation makes the colossal problem manageable, allowing your desktop computer to simulate the grand dance of an entire galaxy. This relentless, step-by-step calculation is the very heartbeat of your creation. It is the engine that transforms your static blueprint and quiet initial conditions into a roaring, dynamic, and living cosmos, allowing you to sit back and witness the impossible, the birth of the very first structures in your universe. Gravity's patient pull now begins to sculpt the void. What started as a nearly smooth distribution of matter, those tiny seeds you planted, now starts to ripple and clump. Under the relentless attraction of its own mass, the diffuse gas and unseen dark matter begin to coalesce, drawing together into a vast, intricate cosmic web. You can watch it happen in your simulation, a process that unfolded over billions of years in our own universe, now compressed into a breathtaking fast forward. Thin filaments of matter stretch across the growing emptiness, connecting at dense nodes like intersections in a spider's silk. These nodes are the first dark matter halos, the gravitational anchors for everything that follows. It is within these halos that the true magic of creation begins. Ordinary gas pulled into these deep gravitational wells starts to cool. As it loses energy, it condenses, collapsing further into swirling disks. Pockets of gas at the center become so incredibly dense and hot that nuclear fusion ignites, and the first stars blaze to life. This is the cosmic dawn, and you have a front-row seat to the birth of the very first proto-galaxies, illuminating the darkness of your young cosmos. This virtual laboratory gives you a unique power, the ability to tweak the nature of the dark matter itself. Is dark matter cold, moving slowly and clumping easily into small, dense halos? Is it warm, with faster-moving particles that suppress the formation of the tiniest structures? Or is it hot, a relic of the early universe that would smooth out small-scale clustering entirely? By changing this single property in your simulation, you can watch how the entire cosmic web changes. A cold, dark matter universe fills with a fine mist of small galaxies, while a warm one might produce a more sparse distribution of larger islands. You are running a direct test on a theory that astronomers are still trying to confirm by peering into the deepest reaches of our own night sky. But why stop at testing theories about our own universe? You have built this cosmos from the ground up, and its boundaries are defined only by the rules you wrote. This is where your digital cosmos becomes a true laboratory for the invisible. Dark matter is the ghost in the cosmic machine, and you now have the power to give that ghost different properties to see which one builds a universe that looks like our own. You can program a reality where dark matter particles barely notice each other, or one where they constantly collide and scatter, like a crowd of people in a packed room. This is known as self-interacting dark matter. In a standard simulation, dark matter piles up into halos with incredibly dense, sharp central peaks. But when you introduce self-interactions, those collisions act like a cosmic pressure, smoothing out the core into a gentler, flatter profile. It is the difference between a mountain with a jagged, Everest-like summit and a rounded, rolling hill. And this is not just a theoretical exercise. Astronomers use telescopes like Hubble and the James Webb to measure the actual distribution of mass within distant galaxies. When they find a galaxy with a large, diffuse core, it becomes a tantalizing piece of evidence that our universe might, in fact, be filled with this self-interacting variety. Your simulation allows you to run this comparison directly, pitting your digital galaxies against those real-world observations. You can go even further, crafting a cosmos where dark matter is unstable and slowly decays into radiation or other particles over billions of years. How would that gradual loss of gravitational anchor reshape the cosmic web over time? Each simulation is a vote, a concrete test that either supports or rules out a different dark matter candidate, bringing the abstract world of particle physics into the clear, visual language of galactic structure. With such control over the invisible scaffolding of the cosmos, a natural next step emerges to manipulate the even more mysterious force that dictates its ultimate fate, dark energy. The ultimate fate of your cosmos rests in the hands of its most enigmatic component, dark energy. This is the force responsible for the accelerating expansion of our own universe, and in your simulation you hold its reins. You can dial its strength up or down, transforming it from a subtle background effect into the dominant force of creation. Crank its influence to an extreme, and something dramatic happens. Long before galaxies can even begin to coalesce, the repulsive push of dark energy overpowers every other force. It doesn't just expand space, it actively shreds the fabric of reality itself, pulling galaxies, stars, and even atoms apart in a catastrophic event cosmologists call the Big Rip. Your universe would end not with a collapse but with a violent, instantaneous tear. Now turn the dial in the opposite direction. Weaken dark energy to a whisper or remove it entirely. In this scenario, gravity is unchallenged. The initial expansion from your Big Bang moment would steadily slow, halt, and then reverse. Every galaxy would begin rushing toward every other, the cosmos heating up as it collapses back into a singular, fiery point, the Big Crunch. These are not just abstract ideas, they are fates you can actively witness unfolding on your screen. But your control extends even further. What if dark energy is not a constant, unchanging force, but one that evolves? This is the core of quintessence models, where dark energy's strength can fluctuate over time, perhaps growing stronger in the future or having been different in the distant past. By programming such a dynamic force into your toy universe, you can test these very theories against the observed acceleration of our own reality. Each simulation becomes a direct probe into why our cosmos is expanding at the precise rate we measure, helping to answer one of the most profound questions in all of physics. Once you have set the grand, sweeping fate of your cosmos, you can turn your attention to the intricate details, to the engineering of individual solar systems and the very stars within them. From the galactic web, we dive into a single, swirling cloud of gas and dust. Zooming into one of those newly formed galaxies, you can now engineer entire solar systems from the ground up. This process begins with a molecular cloud, a vast, cold, and diffuse nursery of hydrogen and complex molecules. In your simulation, you define its mass, its temperature, and most importantly, its spin. Then you introduce a trigger, a shock wave from a nearby supernova or simply the cloud's own growing instability, and set gravity to work. As the cloud collapses, it fragments, breaking apart into dense knots of matter that will become individual stars. Each of these protostars is quickly surrounded by a spinning, flattened disk of leftover material, a protoplanetary disk. This is the raw stuff of worlds, the cosmic construction site where planets are born. Within this churning disk, microscopic dust grains begin to stick together, forming pebbles, then rocks, then planetesimals, the building blocks of planets. The final architecture of the solar system is written in the properties of this initial disk. Its total mass dictates how many planets can form. Its chemical composition, particularly the abundance of heavy elements like iron, silicon, and carbon forged in the hearts of long-dead stars, determines whether those planets are rocky worlds like Earth or gas giants like Jupiter. This is where you gain an incredible power, the ability to rewind our own solar system's history. You can program the conditions of our early solar nebula and test a bold idea like the Grand Tack hypothesis. This theory suggests that young Jupiter migrated inward toward the Sun, only to be pulled back outward by Saturn's gravity, a gravitational dance that would have scattered the inner asteroid belt and shaped the entire inner solar system, perhaps even delivering water to a young, dry Earth. By running this simulation, you can watch this cosmic billiards game play out, seeing if it results in a system that looks like our own. This power to create not just galaxies, but individual worlds, opens the door to the most profound question of all. If you simulate a planet with liquid water, a stable atmosphere, and the right chemical ingredients, could the spark of life ever ignite within your digital universe? The leap from a stable, watery world to a living one is perhaps the greatest transformation in all of nature. Within your simulated planet, you have the power to set the stage for this very drama, to probe the boundary between complex chemistry and the first whispers of biology. This is the frontier of astrobiology in silico, a field that uses computational worlds to test the universal principles that might lead to life. You begin by defining a planetary environment, selecting an atmospheric composition rich in gases like methane, ammonia, and water vapor, a plausible recipe for a young world. You pour a global ocean, and then you introduce the spark energy sources that mimic the violent youth of any planet. Program infrequent lightning strikes that flash through the turbulent skies. Crank up the ultraviolet radiation from the planet's parent star, bathing the surface in a constant, energetic glow. Simulate the intense thermal energy from volcanic vents on the ocean floor. Then you set the simulation in motion and watch the chemistry unfold. You are not tracking every single atom, but modeling the statistical probabilities of molecular interactions. Over eons of simulated time, you might witness the formation of complex organic molecules, the building blocks of life, amino acids could begin to link together. Lipid molecules might spontaneously form hollow, cell-like spheres. This is a digital recreation of the famous Miller-Urey experiment, but on a planetary scale and with near-infinite variations. The profound challenge here is that we do not yet know if the emergence of life is a near certainty given the right conditions, or a fantastically improbable fluke. Your simulation cannot yet create a self-replicating cell, but it can map the chemical pathways that make such an event more or less likely. It forces you to confront fundamental questions. What is the bare minimum definition of life? Is it simply a system that can metabolize energy and replicate itself? Could life be based on a chemistry completely different from our own, using silicon instead of carbon, or liquid methane instead of water? By running these experiments, you are not just building a world, you are testing the very conditions of your own existence, asking whether we are a cosmic accident or an inevitable outcome of universal laws. This powerful tool, once confined to theoretical speculation, is now being deployed to solve active, pressing mysteries in our very own cosmos. This very method is now being deployed to solve one of the most persistent puzzles in modern cosmology, the Hubble Tension. Picture two teams of astronomers using the world's most powerful telescopes. One team peers into the early universe, measuring the cosmic microwave background, the faint afterglow of the Big Bang. From this pristine baby picture, they calculate a specific rate for the universe's expansion. The other team looks at the local, modern universe, observing pulsating stars and exploding supernova to measure that same rate directly. The baffling result is that these two meticulous measurements do not quite agree. The local universe appears to be expanding faster than the early universe's data predicts. It is a small but stubborn discrepancy that could imply something fundamental in our standard model of cosmology is incomplete. This is where your toy cosmoses become a forensic tool. Researchers are not building just one simulation, they are generating millions of them, a vast ensemble of digital universes. In each one, they subtly adjust the underlying physics. They tweak the properties of dark energy, they alter the number of types of neutrinos, or they modify the precise conditions of the primordial plasma. They then run the cosmic clock forward in all these alternate realities, asking a single, critical question. In which of these universes does a Hubble tension naturally emerge? Does the simulated early universe predict a different expansion rate than the simulated modern universe? By comparing this massive library of virtual outcomes to our one real, observed universe, they can perform a kind of cosmic triage. Is the tension a sign of new, unknown physics, a fifth force or a decaying form of dark matter? Or is it merely a colossal statistical fluke, or perhaps a subtle, cumulative error in our observational techniques? Each simulation acts as a rigorous test, a controlled experiment that is impossible to run in the real world. This virtual experimentation provides a concrete pathway to resolve a major conflict, demonstrating that these blueprints are far more than philosophical exercises. They are practical, indispensable tools for diagnosing the health of our most fundamental theories about reality. But why stop at tweaking the constants we know? What happens when we rewrite the very alphabet of the cosmos, altering the fundamental particles that make up everything we see? Our reality's 3 dimensions of space might be just the beginning. String theory, one of the most ambitious frameworks in physics, proposes that the universe could be woven from tiny, vibrating strings existing in many more spatial dimensions, perhaps as many as 11, all curled up into sizes far too small for us to perceive. In your simulated cosmos, you do not have to imagine these hidden realms, you can build them. You can define a universe with 4, 5, or even 11 spatial dimensions and run the experiment to see what happens. The consequences would be immediate and profound, starting with the force that holds the cosmos together, gravity. In our three-dimensional world, gravity weakens with the square of the distance. But in a universe with extra-spatial dimensions, that fundamental law changes. Gravity could leak into these additional directions, weakening much more dramatically over short ranges. This single alteration would rewrite the entire story of cosmic structure. Planets might not be able to form stable orbits, stars could collapse under different rules, and the beautiful, slow dance of galaxy formation might never even begin. The very nature of light would be transformed, its waves propagating through a more complex geometry, creating optical effects and shadows we can scarcely describe. Of course, our human brains are wired for 3 dimensions, making it impossible to truly picture a 4-dimensional cube, a hypercube, let alone an 11-dimensional universe. This is where the simulation becomes our eyes. We cannot visualize the higher dimensional space itself, but we can program its mathematical rules and then observe the consequences in a 3-dimensional projection we can understand. We can watch how matter clusters, how forces behave, and how structures evolve under these exotic laws. This gives us a unique, tangible window into theories that are otherwise purely abstract and untestable. By building these hyperspatial realms, we are not just playing with fantasy, we are conducting rigorous experiments on the nature of reality itself, forcing us to confront a deep and unsettling question. If a simulated universe with different dimensions can feel just as real and consistent as our own, what does that say about the nature of the reality we think we inhabit? Building a cosmos on your own computer does something strange to your perspective. You start to see the universe not as an immutable given, but as a system, one with underlying rules and potential shortcuts. This line of thinking inevitably brushes up against one of the most mind-bending ideas in modern thought, the simulation hypothesis. What if our own reality, with all its richness and depth, is itself a sophisticated simulation running on some unfathomably advanced computer in another, truer reality? This is not a new proof, but a philosophical speculation. Yet, by building these models, we gain a tangible, almost intimate sense of how a simulated reality might actually function. We confront the very limitations that would constrain any creator. The most obvious is computational resolution. In your own simulation, you cannot track every single subatomic particle. You have to group matter into discrete chunks, into what are effectively pixels of reality. There is a fundamental grain size to your cosmos, a smallest possible unit of space and time below which your simulation cannot see. Does our own universe have such a fundamental grain? Is the Planck length the smallest meaningful measurement in physics, evidence of our own reality's pixel size? Then there is the necessity of simplifying assumptions. To make a galaxy simulation run in a reasonable amount of time, you use approximations for the gravity of distant star clusters. You do not render a forest by modeling every leaf and beetle. You create a statistical representation of it. A super-advanced simulator of our own universe might do the same, only rendering the fine details of a quantum system or a distant planet when an observer is actually looking. These are not flaws in the model, they are necessary engineering choices. This hands-on experience does not prove we are in a simulation, but it gives the idea a concrete framework. It moves the concept from pure science fiction into a domain we can discuss with the language of computer science and physics. We can ask practical questions about what signatures a simulated universe might possess. Would the laws of physics show signs of being discrete and mathematical at their core, which they do? Would there be hard limits on processing speed, like the speed of light, that prevent information from moving too quickly and overloading the system? In building these toy cosmoses, we find ourselves in a peculiar position, simultaneously the creator of a tiny digital reality and a potential creation within a vast one. The line between the two begins to blur, leaving us to wonder about the nature of our own reality. This profound shift in thinking is now accessible to anyone with a computer and a spark of curiosity, using tools that are freely available to start crafting universes today. Your first step into universe building is choosing the right digital workshop. For a beginner, the most accessible doorway is a program like Universe Sandbox. Think of it as a cosmic sandbox in the most literal sense, a visually rich playground where you can drag and drop planets, ignite stars into supernova, and watch entire galaxies collide, all in real time. Its power lies in a user-friendly interface that puts gravity and orbital mechanics at your fingertips, making the fundamental forces of the cosmos feel intuitive and immediate. It is the perfect tool for casual exploration and for developing a visceral understanding of how celestial objects interact. But if your ambition is to run rigorous tests on dark matter or the physics of the early universe, you will need to graduate to the tools used by professional cosmologists. This is where you encounter powerful, open-source codes with names like Gadget and ENSO. Gadget is a workhorse for cosmological n-body simulations, which essentially means it is masterful at tracking the gravitational dance of billions of particles, whether they represent dark matter halos or individual stars. ENSO, on the other hand, specializes in astrophysical fluid dynamics, simulating the complex behavior of cosmic gas, the formation of shock waves, and the intricate feedback from stars and black holes. Harnessing these professional tools usually requires some comfort with programming languages like C++ or Python, as you will be modifying configuration files and scripts to define your universe's unique parameters. This initial choice ultimately hinges on your goal. Are you looking for an inspiring digital toy to satisfy your curiosity? Or are you ready to get your hands dirty with code to contribute to the frontier of cosmological research? Either path is valid, and both begin with this single, practical decision. With your software selected, the empty stage of your cosmos is ready for its first inhabitants. Once your universe is populated, the real challenge begins, the delicate art of modeling its two primary ingredients. One is the ordinary matter that builds everything we can see, from stars to our own bodies, known as baryonic matter. The other is the invisible, mysterious substance that holds it all together, dark matter. Think of them as the actors and the stagehands in your cosmic play. The baryons are the luminous stars delivering their lines on stage, while the dark matter is the unseen crew moving the sets and holding the entire theater together with ropes and pulleys of pure gravity. To create a simulation that feels real, you must give each of these components their own distinct set of rules. Dark matter is, in some ways, the easier of the two to program. Since it seems to interact only through gravity and not at all with light, you can model it as a vast collection of simple, collisionless particles. They feel each other's gravitational pull, they move in response, but they pass through one another like ghosts in the night, their collective dance weaving the invisible skeleton of the cosmic web. Baryonic matter, however, is a chaotic and messy affair. This is the stuff of gas and plasma, and it obeys the complex laws of hydrodynamics. You are no longer just tracking gravity, you are simulating pressure waves, shock fronts from exploding stars, and the intricate cycle of heating and cooling. A cloud of gas might collapse under its own weight, heat up from the pressure, then cool by radiating energy away, allowing it to collapse further and eventually ignite into a star. That star will then live out its life and potentially die in a supernova, blasting enriched material and immense energy back into the surrounding gas, stirring it up and seeding the next generation of stars. This entire feedback loop is what makes galaxies look the way they do, and simulating it accurately is one of the grandest challenges in all of computational astrophysics. To manage this complexity, many simulations use a hybrid approach. They represent the dark matter as millions of individual particles, while treating the baryonic gas as a single, continuous fluid, tracking its density, temperature, and velocity at every point in a computational grid. This marriage of two different modeling techniques allows you to capture the gravitational dominance of the dark matter while still simulating the rich, transformative physics of the ordinary matter that actually lights up the universe. The true test of your skill comes after the simulation has run, when you must learn to read the story it has told. You will analyze vast data sets, creating maps of dark matter density and comparing them to the luminous distribution of simulated galaxies. You might find that without the right supernova feedback, your simulated galaxies form too many stars too quickly, becoming far brighter and more massive than any we observe in the real universe. Or you might discover that the specific way dark matter clumps on small scales directly influences the number of tiny, dwarf galaxies that orbit a larger one. This process of creation, analysis, and comparison is how we refine our blueprints, slowly tuning our simulated universes until they not only look like our own, but truly help us understand why it had to be this way. The true power of your simulation is unlocked only when you can see its story. After the supercomputers have finished their calculations, you are left with mountains of data, terabytes upon terabytes listing the precise positions, velocities, and densities of billions of digital particles. It is a cosmic census of unimaginable scale, a raw, unreadable ledger of creation. This is where the final, crucial tool comes into play: data visualization. Specialized software like the Python library known simply as YT becomes your window into this digital cosmos. With it, you can command the data to reveal its secrets. You can generate breathtaking three-dimensional renderings of the entire cosmic web, a luminous, intricate neural network of dark matter stretching across the void. You can take a virtual knife and slice clean through a simulated galaxy, peering into its bustling core and its sparse halo to see how matter is distributed. You can compile these snapshots into a movie, watching billions of years of galactic evolution unfold before your eyes in a matter of seconds. This transformation from raw numbers to visual narrative is more than just pretty pictures. It is the very act of scientific discovery. But to truly test your universe, you must go deeper into the realm of statistical analysis. You need to ask quantitative questions. Does the distribution of galaxies in my simulation match the one we see in our sky? To answer this, you might calculate something called the power spectrum. Think of this as a cosmic barcode, a mathematical measure that describes how matter clumps together on different scales, from the vast filaments of the web down to the tiny dwarf galaxies. By comparing your simulation's power spectrum to the one measured by telescopes like the Sloan Digital Sky Survey, you get a rigorous numerical grade for your cosmic blueprint. Does it match reality, or does it reveal a flaw in your assumptions about dark matter or the initial conditions? This entire process, from the first line of code to the final, shimmering visualization, completes the loop of modern cosmology. It transforms abstract programming into tangible, testable science, allowing you to witness the direct consequences of the laws you wrote. With this powerful pipeline now fully assembled, researchers are deploying it to crack open the most stubborn mysteries in the cosmos, from the violent lives of galaxies to the nature of spacetime itself. For decades, the theoretical blueprints for galaxy formation were missing a crucial piece. Astronomers could chart the majestic spirals and blazing ellipticals, but they could not fully explain why galaxies stopped growing. Observations showed a clear limit, a ceiling on galactic size that theory alone could not justify. Then, simulations gave us eyes to see the invisible regulator, the supermassive black hole at the galactic core. These are not the passive monsters we once imagined. In a digital universe, you can watch one feed. As it accretes a swirling disk of gas and dust, the black hole does not quietly consume everything. Instead, it can transform that gravitational energy into a titanic cosmic wind. This is active galactic nucleus feedback, a process where the black hole effectively blows a powerful bubble of ultra-hot gas into its surroundings. That heated gas cannot cool down, and without cool gas, new stars cannot form. The galaxy's growth is stifled from within. This discovery, vividly illustrated in landmark simulations like Illustris TNG, solved the mystery of the missing giant galaxies. It revealed a delicate balancing act, a self-regulating feedback loop where a galaxy's own central black hole governs its final size. Without the ability to watch this dynamic play out over billions of years in a virtual cosmos, this complex dance would remain a theoretical guess. These toy universes have provided the coherent narrative for galaxy evolution we desperately needed, a story that now allows us to forecast the ultimate fate of our own Milky Way as it continues its long, slow dance with the colossal black hole at its heart. The ultimate fate of our own cosmic home is written in the gravitational code of a simulation. We know with startling certainty that in about 4.5 billion years, the Milky Way and the Andromeda galaxy will begin their long, slow, and inevitable collision. In your digital universe, you can fast forward through this epic, watching the two great spirals first stretch toward each other, drawn by gravity's unrelenting pull. They will not crash head-on, but swing past each other in a breathtaking gravitational dance, their spiral arms tearing apart into great streams of stars. Over billions of years, they will swing back again and again, their momentum slowly bleeding away until they finally settle into a single, massive, blob-like elliptical galaxy, a new cosmic island that astronomers have nicknamed Andromeda. The sheer scale of this event is what makes simulation so vital. While the galaxies merge, the vast emptiness between stars means direct collisions are incredibly rare. Your simulation will show you that most stars are simply tossed onto new, wildly different orbits, like feathers caught in a gentle but chaotic whirlwind. And you can track a single, specific star, our own sun. You can assign it a digital tag and watch its probable fate unfold. Will it be flung out into the cold, dark emptiness of intergalactic space, or will it find a new, stable orbit within the glowing core of Andromeda? The simulation provides the answer, transforming a distant, abstract future into a visual certainty you can explore from every angle. This predictive power is not limited to the grandest scales of galaxies. That same curiosity now compels us to shrink our focus, to build a cosmos not of stars but of probabilities where the very rules of reality become fuzzy and strange. To build a cosmos that truly mirrors our own, you must become a master of chaos, seeding your pristine digital void with a very specific kind of imperfection. The largest structures we see today, the vast clusters of galaxies stretching across billions of light years, did not emerge from a perfect, smooth beginning. Their origins lie in the frantic, probabilistic realm of the quantum world, in the fleeting fluctuations of energy that bubbled up in the first fraction of a second after the Big Bang. To capture this in your simulation, you cannot simply paint in galaxies by hand. You must program the very ghost of creation itself, injecting a random, Gaussian field of density perturbations into your initial conditions. This term, Gaussian, simply means the fluctuations follow a particular statistical pattern, a bell curve where most regions are only slightly denser or thinner than average, with a few rare, extreme peaks and valleys scattered throughout. The precise pattern of these ripples is not arbitrary. It is a direct input from our observations of the cosmic microwave background, that fossilized light from the infant universe. You are essentially using that ancient baby picture as a template, telling your simulation to start with those exact same wrinkles in the fabric of spacetime. This single act introduces a powerful element of genuine randomness and statistics into your creation. No two simulations will ever be exactly alike. Run the same code with the same laws of physics 1,000 times, and each time you will get a unique cosmic web, a different arrangement of galactic filaments and voids, just as no two possible universes in a theoretical multiverse would be identical. One simulation might produce a universe dominated by a single, immense supercluster, while another might be a more even tapestry of medium-sized structures. This tangible link between the unpredictable quantum shake of a single point and the grand classical architecture of the cosmos is one of the most profound insights of modern science. By simulating it, you are not just building a model, you are reinforcing the deep, beautiful unity of physics, demonstrating how the rules governing the smallest particles are inextricably woven into the fate of the largest things we can see. Your digital universe becomes a testament to the idea that our reality, for all its apparent order, is fundamentally a statistical reality, a single roll of the cosmic dice that happen to produce a world we can call home. Running 1,000,000 simulated universes produces a stark and humbling result. The vast majority of them are cosmic graveyards, sterile and dark. You will watch as universes with a slightly stronger nuclear force burn through their hydrogen fuel in a fleeting, brilliant flash, leaving behind nothing but cold helium ash. Others, where gravity is a fraction weaker, will see matter fly apart so rapidly that galaxies never even begin to condense. In this grand computational experiment, universes capable of forging planets, let alone fostering life, are the rarest of exceptions. This is the Anthropic Principle rendered in pure data. We find ourselves in a universe with precisely tuned constants, not because of some special design, but out of sheer necessity. We could not possibly exist in the endless, silent voids that constitute the overwhelming majority of possibilities. This simulation does not answer the deepest why, but it fundamentally reframes the mystery. Instead of asking why our laws are so perfect for life, we are now compelled to ask what kind of cosmic landscape could ever give rise to such a rare and fortunate outlier. Our digital laboratories are the only tools that can map this vast terrain of what might have been, turning a philosophical puzzle into a quantifiable exploration. This line of inquiry naturally pulls us toward the edge of known physics, to a place where the rules themselves become fluid and the nature of reality is up for grabs. Your control over spacetime geometry allows you to engineer the impossible. You can program the fabric of your digital cosmos to twist back on itself, stitching together two distant points with a tunnel, a theoretical wormhole. To build this cosmic shortcut, you must first defy one of the universe's most basic rules. You need to create exotic matter, a substance with a negative energy density. Think of it as a kind of anti-gravity glue, a repulsive force that pushes outward to prop open the wormhole's fragile throat against its own instinct to collapse. In our reality, such matter is almost certainly impossible to manufacture, a phantom from the furthest edges of Einstein's equations. But in your simulation, you can simply define it into existence. You can then watch what happens, observing how this theoretical tunnel responds to the passage of simulated matter or energy. Does it remain stable, or does it shudder and pinch off into a singularity at the slightest disturbance? This is not a blueprint for a real machine, but a profound stress test for the theory of general relativity itself. You are probing the absolute limits of our mathematical understanding of space and time. You can take this exploration a step further into even stranger territory by simulating closed time-like curves. This is the sterile, technical term for a path through spacetime that loops back onto its own past. It is the theoretical foundation for time travel. With this geometry active in your simulation, you can stage the classic paradoxes. What happens if a simulated agent travels back and prevents its own creation? The simulation does not resolve the paradox, but it forces the underlying physics to confront it. Does the system crash? Does it generate a parallel timeline? Or does it simply forbid the action through some as yet unknown law? These exercises are less about building a time machine and more about asking what our current laws of physics truly allow and where they ultimately break down. After stretching the fabric of reality to its theoretical limits, we can bring this power back to a more human scale, to the classroom. This educational power transforms the most abstract cosmic principles into tangible, interactive experiences. A student can take the helm of a simulated solar system and discover for themselves why planets move in ellipses, not circles. They can crank up the mass of a star and watch, in real time, as its gravitational grip tightens, pulling a nearby world into a faster, tighter orbit. They can gently nudge an asteroid and witness the delicate chaos of orbital resonance, seeing how a tiny push can lead to a dramatic shift over millions of simulated years. This is learning through direct manipulation, where cause and effect are no longer just words in a textbook but a visceral, visual dance unfolding on the screen. The concept of tidal forces, often a dry and difficult topic, becomes immediate when you can drag a moon closer to its planet and watch the world's crust stretch and buckle, its oceans swelling in response to the gravitational pull. This hands-on experimentation builds an intuitive sense of physics that lectures alone can never achieve. Platforms like Space Engine take this a step further, offering a gateway to the entire observable universe built on real astronomical data. A user is no longer confined to a single solar system. They can pilot a virtual starship out of the Milky Way, dive into the Andromeda galaxy, and land on the surface of a hypothetical exoplanet orbiting a distant star. The rings of Saturn are not a static image, but a structure you can fly through. The scale of a nebula is not a number, but a vast cloud you can lose yourself within. This is more than a game. It is a form of cosmic cartography that democratizes the universe, making its wonders accessible to anyone with a computer. It inspires not by telling, but by allowing exploration, sparking the kind of raw curiosity that has fueled scientists for centuries. This power to ignite wonder demonstrates that these simulated universes are far more than research tools for experts. They are a new medium for public science, a way to bring the grandest questions of cosmology directly into the classroom and the living room. The power to build universes is no longer locked away in supercomputing centers. Your own laptop can now become a laboratory for cosmology, thanks to a global movement known as citizen science. Projects like Cosmology at Home harness the collective might of thousands of personal computers around the world. When your machine is idle, it can download a small piece of a massive cosmological simulation, run the calculations overnight, and send the results back to researchers. This creates a distributed supercomputer of staggering scale, tackling problems that would take a single institution centuries to solve. imagine a researcher wanting to test 10 million different combinations of dark matter and dark energy properties. A single powerful computer might take a lifetime to run them all, but a network of 50,000 volunteers can complete the task in weeks. This crowdsourced power enables vast parameter studies, exploring the entire landscape of possible universes to see which ones look like our own. Beyond just donating processing power, some platforms invite you to become a universe architect yourself. You can log into a web portal, adjust sliders for the strength of fundamental forces, set your preferred initial conditions, and launch your own custom cosmos into being. You can then share your results, your most bizarre or beautiful creations, with a community of fellow enthusiasts. One person might design a universe where stars are 1,000 times brighter, while another tests a reality with no weak nuclear force. This collaborative playground for amateur cosmologists accelerates discovery in a way professional science alone never could, fostering a global community united by a shared curiosity about our cosmic origins. It is a powerful reminder that you do not need a PhD to contribute to humanity's grandest questions. Yet, as this power to create becomes democratized, we must pause to consider its profound implications and inherent limitations. We are playing with the ultimate set of building blocks, and with that creative power comes a deep ethical responsibility. Even our most ambitious digital universes are built with pixels of a certain size. We face a fundamental trade-off, a triangle of constraints where we can only ever maximize two corners at the expense of the third. You can simulate a vast volume of space, but to do so you must sacrifice the fine resolution needed to see individual stars. You can include incredibly complex physics, like magnetic fields and supernova feedback, but that forces you to shrink the simulated volume down to a single galaxy. Or you can achieve high resolution across a large volume, but only by simplifying the physics so dramatically that you are left with a universe of ghostly particles that never ignite into stars. Every simulation is a negotiation, a carefully chosen compromise that answers a specific question while ignoring countless others. Beyond these computational limits lies a more profound boundary, the frontier of our own imagination. We can only program the physics we have already mathematically described. A simulation is a test of our existing ideas, a way to ask whether this particular set of rules builds a world that looks like home. It cannot invent a new force of nature or dream up a form of dark energy we have not yet conceived. The digital cosmos is a brilliant mirror, but it can only reflect the light we shine into it. This inherent limitation demands a deep humility. We must always remember that a beautiful, self-consistent simulation is not necessarily a true one. Its success might simply mean we are clever enough to build a compelling digital story, not that we have uncovered the ultimate blueprint of reality. This careful, responsible interpretation of our own creations is the most important skill a universe builder can learn, and it naturally leads to a final, weighty consideration. What is our responsibility when we hold this power to craft entire realities, even simplified ones, in the palm of our hand? The act of creation always comes with a cost, and not just in processing cycles. As we sculpt entire cosmoses from lines of code, we step into a role laden with profound philosophical weight. The sheer power to define reality for a digital domain forces us to consider the moral dimensions of our own creative impulse. For now, the conscious inhabitants of our simulations are purely theoretical, but the ethical framework must be built long before the first digital spark of awareness might flicker. This is not just a question for cosmologists, it mirrors the core debates in artificial intelligence ethics. If a system becomes sufficiently complex, imbued with a rich inner world of experience, What duties does its creator hold? Are we responsible for the well-being of minds we might one day birth inside a machine? While that remains a distant horizon, our immediate responsibility is far more tangible, rooted in the physical world our servers inhabit. These vast computational models consume immense energy, drawing power from the very real planet we call home. The ethical choice is to ensure that every kilowatt expended serves the highest purpose, the relentless pursuit of understanding the cosmos we are a part of, rather than a mere exercise in virtual dominion. The goal is enlightenment, not control. Our blueprints should be tools for asking better questions, not for playing God in a sandbox of our own design. This forward-looking responsibility extends to the very future of the field, where the line between simulating a universe and perhaps even creating one grows ever more intriguing. The next leap in universe building will not be written by human hands alone. Artificial intelligence is stepping into the role of a cosmic architect, capable of exploring a near-infinite landscape of possible realities. This vast expanse of what-ifs is known as the parameter space, a multidimensional map where every point represents a unique universe with a different combination of physical constants and laws. For a human, searching this space is like trying to find a single, specific grain of sand on every beach on Earth. It is a hopeless task, but an AI can navigate this cosmic library with breathtaking speed, running thousands of simulations in parallel, learning from each result, and intelligently steering itself toward the most promising and puzzling models. It might stumble upon a strange, stable universe where time flows backwards in certain regions, or one where dark matter forms intricate, ring-like structures instead of halos. These are possibilities a human programmer, constrained by intuition and bias, might never think to test. This partnership between human curiosity and machine learning is accelerating discovery, turning the hunt for viable cosmologies into a guided tour of the multiverse. At the same time, the raw engine of computation is undergoing its own revolution with the dawn of exascale computing. These next-generation machines can perform a quintillion calculations per second, a number so vast it defies everyday comprehension. This power will fuel simulations of a fidelity we have only dreamed of. We will no longer have to approximate an entire galaxy as a cloud of points. We will be able to watch individual stars ignite within swirling gas clouds, trace the intricate magnetic fields that channel matter into newborn solar systems, and witness the violent jets erupting from supermassive black holes in stunning, dynamic detail. The line between the simulation and the reality it seeks to emulate will begin to genuinely blur. The ultimate expression of this ambition is the creation of a digital twin, a perfect, one-to-one replica of our entire observable universe. This would not be a toy cosmos with simplified rules, but a monumental copy built upon our most precise measurements, from the precise ripple pattern of the cosmic microwave background to the exact location and motion of billions of galaxies. Within this ultimate sandbox, we could run the ultimate experiments. We could rewind time to the first microsecond with absolute confidence, or fast forward to witness the ultimate fate of the Andromeda galaxy collision in perfect detail. We could test the most subtle implications of string theory or alternative models of gravity by asking the digital twin to show us what their cosmic signatures would look like. This journey, which began with philosophers sketching worlds with logic and pen, is now accelerating toward an unimaginable horizon. The humble toy cosmos has grown up, and its potential to reveal the deepest secrets of existence is only just beginning to unfold. From a philosopher's thought experiment to a physicist's most powerful tool, these digital blueprints have transformed our very relationship with the cosmos. We no longer gaze at the stars as passive observers, but as active participants in a grand experiment, testing the boldest ideas about dark matter, cosmic evolution, and the fundamental laws of physics without ever needing a telescope. This journey has taken us from solving the stubborn Hubble tension to forecasting the collision of galaxies, from igniting virtual stars in a classroom to crowdsourcing the exploration of the multiverse from our living rooms. The most profound shift, however, is not in the answers we have found, but in the new questions we are empowered to ask. Each time you hit run on a simulation, you step into a role far greater than that of a scientist. You become a creator, a universe builder holding a single, luminous thread of code that unravels into an entire cosmos of infinite possibilities. This digital frontier has turned the entire universe into a dynamic, interactive canvas, limited only by the scope of our curiosity. So we have to wonder, with this unprecedented power now at your fingertips, what kind of universe will you choose to paint first? Share your most creative cosmic ideas in the comments below, and join us as we continue our journey to the very